Welcome to our video series on logistic regression. This is our video on simple logistic regression using an independent variable that is continuous. So, to start off, we're going to load the packages dplyr, rocker, ggplot2, and caret. And I'm going to be working with a dataset I have called Heart. Basically, it contains a binary variable called num that indicates whether a person is at risk for heart disease or not. Specifically, a 0 means that they have less than 50% of diameter narrowing in their valves, and a 1 means that they have greater than 50% diameter narrowing. We'll also be working with a variable called traced BPS, which I'm just going to refer to as blood pressure. It is the resting blood pressure that a person has. So we will not be centering this trace BPS variable because we're not going to be interpreting the intercept. So this is what our data looks like. It is either a 0 or a 1 for the y variable, and the x variable is continuous, going from about 90 to 200. You can see that there's a lot of overlap. There's no clear distinct groups that we're getting, so our model will probably not be super accurate, but we are only using one variable to make it. So I will start by setting the seed to be equal to 1, and then we are going to make a training data set and a test data set. The training data set will be 2/3 of our data, and it will be used to make our model, and the test data set will be 1/3, and it will be saved later for testing our model. So we're going to make the model using the GLM function. It's actually very similar to making a regular linear model. You put your y variable, then you put the twiddle, and you put your x variable that you want to use, or you could do more, which we'll cover in a later video. You set your data equal to the data set you're using, and you set the family to binomial. You have to do this when you're making a binary model, or else the code just won't run. And then you set your subset to be equal to the training data set. So now we can take a look at our model. We do this by using the summary function, just like you would with a linear model once again. And the output is very similar. So it gives us an estimate for our trace BPS, and it looks like it is significant. And the way that you would interpret these betas is by exponentiating them. That's just the way that a logistic model works. So you exponentiate it, and this number, the 1.017, is the increase in the odds of being at risk of heart disease as blood pressure increases by 1. And if we just convert that to probability, we will get that for each 1 unit increase in blood pressure, you have a 0.017 increase in probability of being at risk for heart disease. And that definitely makes sense, because blood pressure is definitely a indicator of heart disease. So now we will assume that your model is going to be what you want, and we will go on with how to use it. So now that we have our model, we can go on and see how it does making predictions. First off, we can see how it makes predictions by looking at its S-curve. So first off, you put the blood pressure variable, the num variable, and into a data frame, and you also put in the fitted values from your model. Then we make a plot. So this looks very similar to the plot we made earlier. In this case, we just added a line with the fitted values. So all these fitted values are between 0.25 and 0.75, it looks like. Usually you hope to have some that are around 1 and 0 to make a cleaner model, but in this case we do not have that. There is some separation between these two levels. At 0 you have some that are closer to a lower blood pressure, and 1 it kind of goes slightly higher, but it's not that big of a difference. So that's just because of the variables that we have chosen. Now we will continue on and make some actual predictions. So let's go down here and make predictions for the data that we did not use to make the model, and by that I mean the testing data set. So we do that by using the predict function, and then we throw in our model, and then we are predicting for all the values that are not in heart train, and you do it as a response. So we're going to do that, and then we're going to take a look at how this comes out. So our predictions are all between, well, here it looks like it's between 0.39 and 0.61. There are probably more values. What we hope is that they are close to the actual values of 0 and 1. That does not always happen. What we're going to have to do is decide a cutoff point for when we round these predictions. We will have to turn them into a 0 or a 1, and the cutoff point will help us find that. So now we're going to go ahead and find that cutoff value. So we need to find this cutoff value for what probabilities will be at risk and not at risk. This is done by maximizing the sensitivity and the specificity. So we do this by looking at a graph of all the possible sensitivities and the specificities, and we get those from the performance function, and you choose sens and spec respectively. And then we're going to graph these and find the point where they intersect. This point maximizes sensitivity and specificity and makes it so that our model will not be biased towards positives or negatives. So to me it looks like 0.44 is going to be the intersection. We can get an exact value. We do not need to do this because everything we do is an estimation anyways, but if we want an exact value, we can put the sensitivity and the specificities all into one data frame together and use the identify function. We go ahead and run this, and then you click the point that it looks like the closest point to where they intersect. So once again, this is also an estimation. I'm going to click that, and it says point number 18 in our send spec data frame is going to have the X value that should be our cutoff point. And it looks like it is 0.44. So we're going to go ahead and use 0.44 as our cutoff point this time. So now we can go ahead and make a graph of our probabilities and predictions and see how well our model is doing. So you can go down here and put our predictions into one data frame, the truths into one data frame, and I'm going to change the labels of the truths from 0 and 1 to no risk and risk, just to make things easier to interpret. And then we're going to make another plot where we plot the predictions and see how well we're going to do. So usually this would be a straight column of points. I have used the jitter function just to give us a better visualization of what this looks like. So what we want is for no risk to all be below the line, and we want risk to be above the line because risk is considered a 1 and no risk is considered a 0. It looks like that is not the case this time. It looks like half and half above and below the line. So this model isn't the best at making predictions, but that is true where we're only using one variable. So we can get the actual values of the sensitivity and the specificity by using the confusion matrix function. So first I'm going to make a new variable that is going to do the rounding of our predictions. So if it is less than our cutoff point, it's going to be a 0, and if it's greater than, it will be a 1. And then I'm going to change that into no risk for 0 and risk for 1. And then we use confusion matrix, and we put the predicted class and the actual truths. And I'm making a positive as being risk, because you're probably going to be trying to predict if someone's at risk of heart disease versus not at risk. So it looks like our overall accuracy is going to be 0.58, and our sensitivity is 0.55 with a specificity of 0.61. And the accuracy is just the average of the sensitivity and specificity. So it looks like we have very close sensitivities and specificities. We tried to balance it as much as we could. This model was okay for just being one variable. Like a greater than 50% accuracy rate isn't the worst thing. So overall, we had a decent looking model, and in the next video, we will cover a model with more variables to see if we can make something more accurate.